So we've talked about differential equations, and why they're called differential equations is because we're talking about differentials. So if you had me for Calc 1, you definitely know what a differential is. If you didn't have me for Calc 1, then I'm sorry. Maybe I'll make a connection for you so you can see it real quick. I'm just going to go off on a little tangent for a quick second for those of you who don't know or didn't have me for Calc 1 and maybe didn't have it covered in that class. So just real quick off of a sketch, if I have a curve and it goes like this, right? And I'm going to use a blue, say this blue here, and I create a tangent line that goes through that. Try to make it straight. Ah, dang it. I wanted it to go straight, but I didn't want it to glitch like that. Okay, so if it touches the tangent there, and I wanted to see at some point here, I wanted to look at the difference between these. It's easy to see. Let me just show you. Okay, so we're going to make a triangle, and I want to use a different color for this triangle. So we can see that from here to our second blue dot, this is the distance that's covered, right? This would be my actual y value, and this would be the tangential approximation, right? If I used that, if I use the tangent line to do an approximation of it, correct? Now, from here, what's happening is this vertical distance that we have for this triangle that's created. What do we notice? Don't the approximations for y and the actual y fall in line? And since they fall in line, the change in x is equal to the differential x. Now, the interesting piece is that the actual change in y is this, correct? But this here is the differential y. So this goes back to chapter 3, and it should have been something that was discussed with you in your course. Is this something that you all saw?
Yeah.
Okay, so you understand the difference between, we know that delta x and dx are always equal in this example, and then we also know that delta y and the differential y aren't necessarily the same, right? There is some margin of error there. So that's important. So that's the connection for the dy dx that we're going to be playing with, okay? So just wanted to do a quick rewind for some of you. All right. Now, going to this problem then, it's asking us to solve the differential equation. And so what we want to do when we have differential equations, we want to align the y variable with the differential y, and we want to align the x variable with the differential x. So for part A here then, having dy dx equal to x squared y squared will then be y squared dy is equal to x squared dx. And then from here, in order to be able to solve these problems, we can integrate both sides. And we're going to get y cubed over 3 is equal to x cubed over 3 plus some constant c. And the reason that we have a constant c there is because these are indefinite integrals, correct? Okay, now we have plus c on both sides, but I just moved it to one side, right? So a constant minus a constant is still some constant, correct? We just don't know what that constant is. Agreed?
Yes.
Okay, so then what I'm going to do is I'm going to multiply by 3. So I'm going to get y cubed is equal to x cubed plus some new constant c. This c is just a different constant c. It's not the same as the previous one, but it's still a constant, so I'm just, who cares, it's just c. All right? Here, though, what we can do is we can solve for y. So I'm going to see that y is equal to the cube root of x cubed plus c. This is the answer to part A. Are we good?
Yep.
Okay. So now for part B then, we can use the initial condition, and the initial condition tells us that when x is 0, y is 2. So using the part A solution that we got, we're going to get 2 is equal to the cube root of 0 cubed plus c. Now we're trying to find out what the specific equation is for this differential. So I'm going to get 2 is equal to the cube root of c. 2 cubed is equal to c, and so we see that c is equal to a. Now that we have that information, we can come up with the specific equation or the specific curve that's going to satisfy this initial condition, and that is y is equal to the cube root of x cubed plus 8. Boom, done. Are we okay with that?
You made it look so easy.
Yeah. Well, I've spent a couple weeks doing this stuff, you know. Yeah, I've done it for a long time. But the gist of the matter is, we for part A, we're looking at a slope field, right? And from that slope field, if I gave you the initial condition like we did before from 9.2, we could have done a good guesstimate of what the curve would have looked like, right? But now we're using calculus techniques to be able to find the specific equation, and then using that equation to solve for our c value, the constant, so that we can get the exact equation when possible. Okay, that may not always be possible, and that's important to know. Okay? Okay, so let's go on to the next problem. And so we can see here, this is again separable. There is no need for manipulation of the equations, so that's good. I'm not going to teach you 9.4. 9.4 would have done some algebraic manipulations to these separable equations, and then you could make them separable. But we're not doing that in this class. It's not part of the requirement for the class. Maybe at the end of the semester, if we have some time, I'll do it for fun. We'll see. Or maybe I'll just do a lecture on it and post it for your pleasure so you can watch it when you want. All right. But in this one, we can see this is clearly separable. The denominator has everything in terms of y. The numerator has everything in terms of x. And so we can separate this quite easily. And so we see we get 2y plus cosine of y dy should equal 6x squared dx. Now, we're going to integrate both sides. That's terrible. And so I'm going to get y squared plus sine of y is equal to 2x cubed plus some constant c. And we notice this is as far as we can get. And the reason that is because it's impossible for us to be able to solve for y explicitly. Does that make sense?
Yes. Because we weren't given initial condition.
That's right. Since we're not given an initial condition, we can't solve for the constant c, but that still wouldn't affect us being able to solve for y exclusively. You can see how would I get y out? There's no method I have algebraically that would allow me to do that. Does that make sense?
Yes.
Okay. So far, 2 examples are pretty straightforward. This is actually a pretty straightforward one. Would you guys like to try it and then I'll do it for you?
Yeah. Yeah, I want to try it.
All right, give it a stab and then I'll do it. Let me know when you're ready.
I'm not sure how far we can take this.
Right? It's like, okay, wait, where do I go? So the goal is, if you can, to solve it exclusively for y. And this one should be one that you can solve for y. Let me help. That should be your first step. right? Making notation that is useful for you. Do you need another hint?
Would we use log in this?
You will need logs.
Would we use an E?
You will?
Alright, I think I'm ready.
Okay. All right, so let's see if you guys can follow along with the thinking. So since I want y with dy and I want x with dx, I see that I can go dy over y is equal to x squared dx, correct?
Yeah.
So then from here, as I integrate both sides, I'm going to get the natural log is equal to x cubed over 3 plus some constant c, correct?
Correct.
Taking e to both sides, I'm going to get the absolute value of y is equal to k e to the x cubed over 3. Agreed?
Oh,
Yeah. Algebra got you, didn't it?
yeah, I get the K.
The reason that is because of power, and I'll just show it and then I'll erase it. That's the same as e to the x cubed over 3 times e to the c. But I don't want to call it c, even though it's going to be a constant. It's an exponential constant, right? It's another constant, but it's to a power. So I just call that k. So it's just k times e to the x cubed over 3. Right? It's understanding your power rules.
Right.
Does that make sense to everyone?
Yep. Yes.
All right, cool. I told you, algebra never goes away. And since we want it to be equal to y, I have to have plus or minus k e to the x cubed over 3. And there's our solution for this one. Is that cool or what?
Yeah, so this was a manipulation one?
Absolutely, right? Well, no, not manipulation. It was easy to be separated. It's just when we got to solving for y, we needed to do some algebraic manipulation. No, there's going to be equations where, like, I'll show you one. This is something like 9-4. Most people end up having problems with problems like this, where you have, like, I don't know, xy plus, how do I want to show this to you so you can see it? Let's say 4y, right? This isn't separable directly without me doing some manipulation to it, correct? So the first thing that I need to do in this example, this is just a tangent for you. I'd have to first manipulate. Now, I can make it separable. So before it's separable, I had to do some algebraic manipulation. This is a very simple case, but it shows what 9-4 would have done.
Okay.
Does that make sense?
Yeah, thank you.
Yeah. separability in this section is going to be right away. Okay. All right. So the next thing that we're going to talk about is actually pretty interesting. Orthogonal trajectories for curves. So every curve has a curve that is orthogonal to it everywhere. So if I have a parabola, there are curves that will always be orthogonal to them. So there's a curve that will be orthogonal to another curve. Isn't that cool? So like typically if you have a hyperbola, an ellipse is orthogonal to it. There are some cool pictures in your book, and I recommend that you look at them so that you can better understand them. But all that's happening here is understanding orthogonality. So what does orthogonal mean?
Perpendicular.
Perpendicular. So one of the important things that we're going to do with this problem here is we need to understand orthogonality. So here we go. So I'm going to take this problem x is equal to ky squared, and I'm going to manipulate it by doing a differential to it. Okay, so I'm going to implicitly differentiate. So I'm going to get 1 is equal to 2yk dy dx. Okay? Now, the problem is going to be set up so that it can become separable. And so what do we know? Well, here, I'll actually do something. Do I know what y is equal to? Do I know what k is equal to? Can I manipulate this to solve for k in terms of x and y?
Yeah.
Yes, I can. So k is going to be equal to x over y squared, correct?
Yep.
So then I'm going to get dy dx is equal to 1 over 2 xy squared y. I should have written it the other way, but okay, whatever, same thing. That's going to give me dy dx is equal to y over 2x. Agreed?
Agreed.
All right, so then from here, isn't this the slope?
Yes.
So then the orthogonal slope, because we know what orthogonality is, the orthogonal slope is going to be a negative 2x over y equals dy dx. Agreed?
Agreed.
Now from here, we're going to do our separability to create an equation, a family of equations, curves, that are orthogonal to x equals ky squared. So I'm going to get a negative 2x dx is equal to y dy. I'll integrate. So negative 2x dx is equal to the integral of y dy, which is going to give me x squared, a negative x squared plus some constant c is equal to y squared
Over 2.
oh yes, over 2, my apologies. Are we good?
Yes.
Okay, then from here then I'm going to get x squared plus y squared over 2 is equal to some constant c. And this is, we can't solve for c because we don't have a specific condition, but this is the equation to the family of curves orthogonal to our equation that we were given. Isn't that cool? I can see if I can show you the picture. Do you guys want to see the picture of what this looks like?
Yes.
I can try to see if I can pull it up. Hold on.
We didn't give them like that or in terms of line.
Oh, no. This one, what kind of a curve is that? Now we're talking about curves, and so we write our curves in their parent function type, right? Does that make sense what I'm saying? So I'll show you this real quick just so you can see it. This is what matters. Shoot, sorry. Here I'm going to change what I'm sharing so you guys can see. This is what the curve would look like. So what we end up having is that blue curve. And you see, can you see my mouse?
Yeah.
Okay, can you see the ellipses, right? The blue, I'm sorry, is the original function that was given. And the ellipses that are created are the orthogonal to the blue. So this was the x equals ky squared. And then the ellipse is what creates orthogonals to every curve of the original function. So the family of ellipses, these specific ellipses, is going to be orthogonal to the family of curves of the x equals ky squared parabolas. Isn't that crazy?
Looks wild.
Yeah, it's pretty crazy. So we can actually do these things mathematically, which is, it's awesome. But at the same time, it's crazy to think how we know that every ellipse that this thing has and every parabola that's created with these equations will be orthogonal to each other. That to me, when I think about every, it's amazing. It isn't just this. It's not a specific case. It's all. I think that's one of the things that drew me into math so much, is that we can do proofs that if this thing works for this, it's going to work for everything, and that to me is just like, wow. Like I can completely speak with certainty, which is so powerful and good. How are you guys feeling about these examples so far? It's not too crazy, right?
Not too bad at all. The graph is crazy though.
And the graph is crazy, yeah, but the mathematics behind it isn't too bad. It's just that it shows the generality of it and how daunting it can be, right? Now, of course, like every good section in mathematics, there's difficulties that come along. So I said I was only going to do 5 examples, and I've only used about 30 minutes of the class so far. So that tells you something about the next problem, doesn't it?
Yeah.
And here
Get
it
ready
is.
for brain fog then.
It's actually really not that bad. It's more of some of the things that I'll teach you in this example here. The word problems always get people, right? But if we can understand some basics, it won't be too bad. So let's look at this problem and then let's think about it in terms of common sense. And we'll see if we can come about solving it. And I'm gonna try to solve it for you in a way that is very much a layman's kind of common sense way. Okay. So here's what the problem says. It says a tank contains 20 kilograms of salt dissolved in 5,000 liters of water. A brine that contains 0.03 kilograms of salt per liter of water enters the tank at a rate of 25 liters per minute. The solution is kept thoroughly mixed and drains from the tank at the exact same rate. So the rate that's going in is 25 liters per minute. The rate going out is 25 meters per minute. And how much salt remains in the tank after half an hour. Now, one of the key parts to this problem, it doesn't seem like it's a very key piece, but it's this. Since it is thoroughly mixed, that means that the contents of the salt being poured in are ever changing the amount of salt that we have, right? But since it's thoroughly mixed, the amount that is being poured out is a thoroughly mixed solution, brine, containing the salt. Does that make sense?
Yeah.
Okay. Now, we have some important information. Before anything is poured into the tank, what are we looking for in this problem? What is the question that's being asked?
How much salt is accumulated?
We're looking for salt, right? That's everything. So this problem obviously has to do with time. So whatever our problem ends up being, it's going to be a problem with respect to time. Agreed?
Yes.
Okay. Now, initially, we have 0 time. And in 0 time, what we care about is salt. How much salt do we have when we started?
20 kilograms. Twink.
Everyone agree with that?
Yes.
The problem is asking for how much salt we have when?
Half an hour. After half an hour.
After half an hour. So at that half an hour mark. Here is something that's important. Do I write it this way or this way?
30.
We're going to use the 30. Why?
Because it helps with the
It was given in.
minutes.
Yeah, exactly.
That's right. The ratio of water being poured in, the brine being poured in, was in terms of minutes. And I don't want to play with changing it to hours. So, boom. But it's something that I wanted to ask because it's important. Sometimes people want to deal with hours and they need to know that if you're going to play in terms of hours, you need to manipulate the rates that was given. Then it would change your numbers, correct? So we're going to go after and find this. And we're going to see how much salt we're going to end up with. Okay? Now there's something that's important about these problems when we have mixture problems. whenever we have mixture problems, to be able to find the rate of change will be given by a derivative dy dt will be equal to the rate in minus the rate out. That's important. Okay? This is the equation that you will need with any of these types of problems. Rate in minus rate out. Do you think that I'm going to put a problem like this on the exam?
For sure. Yep.
You better believe it. It's coming. So this boxed thing is something that you're going to want to have on your paper. But you need to know what it means, right? So the rate in our problem is what?
25 liters per minute.
Okay. It is 25 liters per minute. But what are we looking for? What's in those liters per minute? Remember, what are we going after?
Salt.
Salt.
6.03 kilograms of salt.
So we need to have 0.03 kilograms per liter. Right? That's how much is being thrown in at that rate. So how much salt is being thrown in? You notice that when we're looking at this rate in, the liters are gone. We're going to have kilograms per minute. And kilograms per minute is telling us about the amount of salt that's being thrown in. Do you see that? So we're getting 0.075 kilograms per minute. But kilograms of what? Salt. Does that make sense to everyone?
Yes.
But something's happening the other way too. Because if we didn't have anything going out, this eventually would become some overflow or just become a massive just amount of salt. So this is where it's difficult for a lot of people. The rate out, we can get the easy part, right? This is 25 liters per minute is going out. Our function, I told you, was going to be a y of t function, correct?
Correct.
And the y of t was representing what?
With respect to time.
Well, it was with respect to time, but it was to deal with what specifically?
The amount of salt with respect to time?
Salt. Again, salt. So we're going to get our y of t, our function that we're looking for, over the container that has the salt in it also has fluid in it, correct? How much fluid is in the container from the get-go?
5,000
So we have 5,000.
liters.
And it's going to be kilograms over liters. Right? Because again, what we're ending up with is some function that's dealing with salt. Are we okay? So I've been able to find the rate in and the rate out. Typically, the rate out is always going to be something like the function over the total amount of fluids. That's typically what it's going to be with the rate being poured in or out. Okay? Now we're going to use this differential. So the rate of change of salt, right, because that's what we're talking about, that's what y represents, is going to be 0.75 minus the amount of salt with respect to time divided by 200. And we can clean that up, right? So we can go dy dt is 150 minus y of t over 200. Now you don't have to put y of t, you could have just put y if you wanted. For simplicity's sake, I'm just going to go with y going forward, okay? Understanding that y is a function. Are you guys okay with that?
Yeah. Yes.
So this is equivalent. Agreed?
Yes.
All right. So now with the differential, what's going to go where? Because this is the important piece, right? What's going to go? I'll do the hard part. Here's dy. Here's dt. What goes with dy?
$150 minus y.
Okay. Where is that?
Top.
Right.
It's in the numerator on the fraction, but it should end up in the denominator with the dy. And this ends up 1 over 200, correct?
Correct.
Is there any confusion on that?
Can you explain that to me, please? I'm confused about it.
Sure. So I have dy dt is equal to 150 minus y over 200, right? I need this with y to be with dy. So that means I'm going to I'm going to divide by 150 minus y and multiply by dt to the other side. So they're going to, in effect, switch positions. So I end up with dy over 150 minus y is equal to dt over 200. Does that make sense?
Okay, yes, that makes sense.
All I did was change the ratio, right? So it's everything on one side's in terms of y and the other one's in terms of dt. The constant is in terms of t, right?
Right.
Okay, cool. Thank you for asking. I know some people, they don't want to ask, but it's like, I probably need that, but I'm not going to ask. Now, when I take the integral of both sides, I'll do the hard part. Can you guys tell me what the left side is? Don't worry, I'll wait.
Is it ln of 1?
Yeah.
Close.
Negative?
It's got to be negative ln of 150 minus y. Does everyone see why it's a negative?
Says it's a fraction, or it's the denominator.
Well,
Because of the y, right? It's minus 1.
correct. Because it's minus y when you do this integral, the u sub that you would have done gets you a negative dy. Does that make sense to everyone?
Yes.
Okay. Just making sure. Making sure. Okay, then from here, let's solve for c. Okay, and I'm not going to move the negative with the negative ln yet, because that could impact my answer. And so that's an important thing to say. When you're going to solve for C, don't distribute the negative over because you'll lose the sign of C. Does that make sense what I'm saying? Or do you want me to demonstrate so you guys can see where the fatal flaw can happen?
Can you demonstrate?
So,
yeah, please demonstrate.
So this will mess you up. Okay? If I'd have gone ln of 150 minus y is equal to a negative 1 over 200t, that's still going to stay at a plus c. I mean, it'll still work. It's just your answer will look a little bit different. So I shouldn't say wrong as much as if they ask you specifically for C, they may mark you wrong. Because the initial condition that was given to us was y of 0 is equal to 20, right? So if I plug in 20, I'm going to get negative ln of a minus 150 minus, my y should be 20, is equal to 1 over 20 times 0 plus some constant c. And we see that c here ends up being a negative ln of 130. If I'd done it on this side, don't I end up with ln of 150 minus 20 is equal to 0 plus c. So c ends up being ln of 130.
Correct.
So if they ask you for the constant c, you might have a sign issue. That's why I don't move any signs until after I've done my initial condition. Okay? It technically doesn't matter, but if the problem is WebAssign could cause issues in terms of having the wrong sign and marking you wrong, and I don't want that to happen to you. So once you get to the point where you're at this position, here is where I would do my substitution of the initial condition. I wouldn't move a sign over or anything like that because that can cause some issues. Okay? And I don't want that to happen to you. That'd be a bummer. Okay, so now we know what C is, and let's see what we can do with that. So going back to the equation, we're going to get negative ln of 150 minus y is equal to 1 over 200t minus ln of 130. Agreed? Now we can do manipulations, and you see that whole negative thing that I talked about is going to become irrelevant at this point. Because look what happens. What's the constant now? Isn't it that positive case? Correct?
Correct.
You see the constants here, but when they ask you for C, they're going to have a negative sign, so that may cause you an issue. That's the only reason why I'm telling you not to do it, because doing it the other way would have led you here anyways, but your C could have had a sign mistake, and I don't want that to happen to you. All right, you ready? Now, in order to be able to solve this, I need to take e of both sides. And that's going to give me 150 130 e to the negative t over 200. Correct? Are we in agreement?
Yes.
Okay, then from here, I'm going to go negative y is equal to 130 e to the negative t over 200 minus 150. And our y is going to be 130 e to the negative t over 200 plus 150. Are we good?
Professor, real quick, could you go back and explain why you used the second row instead of the first row? Basically, you switched the negative over now.
I didn't put this as the negative here. I'm sorry. What's that? Can you repeat that?
Why did you use the positive ln 150 minus 1 instead of negative ln 150 minus 1?
Oh, you're saying from here? Here?
Why did you use that one instead of the one above?
Oh, to go from here to here? Oh, because what I'm trying to do is I'm trying to isolate for y. I'm trying to solve for y. So the very first thing is to get rid of the coefficient.
Oh, okay.
Does that make sense?
Yeah.
Yeah, so that's just to get rid of the coefficient. Let me see. Make sure that I'm correct in everything that I'm doing. Looks good. So remember again that this is y of t is equal to a negative 130 e to the negative t over 200 plus 150, correct?
Right.
That's 150. Okay, now from here then, the problem asked us for a specific time to find out how much salt we were trying to get, right?
Right.
So now what we need to do is plug in that time to find the specific answer. So that was at 30, right? I'm going to need a calculator. So negative 130. Where is my E on this thing? E of negative 30 over 200 plus 150. I get 38.108. And what are these?
Kilograms.
It's just kilograms. So after 30 minutes, the salt content has almost doubled. Isn't that cool?
Pretty cool.
Any questions on the process? We're good? Or are you still trying to absorb? Crickets?
I think I got this.
You're like, wait till I do the homework. Okay. All right.
Exactly.
All right. I'll stop recording here because this is enough. Do you need me to answer any homework questions for you? Or are you still working on homework and you'll wait till Monday? That's fine.
It worked on you.
Okay. All right. Let me. I'll stop recording then.